Okay, now let's start the next session of this morning. The first talk would be the global phase encoding quantum key distribution, presented by Pei Zeng.
So hello everyone, and my name is Pei Zeng. My supervisor is Sean Feng, and from Tsinghua University, and I will introduce some recent progress of MDI-QKD. And my talk is a natural extension of Marco's talk and the former talk. And I think after Marco's talk, everyone can have already get a whole picture of what is MDI-QKD. And I will introduce some recent progress on this topic. And basically on the twin field QKD topic. And so first I will introduce the motivation and the background of our research. And then I will introduce the protocols and give a description of our security proof. And then I will address some practical issues, and I will show the simulation results. And finally, I will give a summary. So what is the motivation? So we know that the most important amount for the QKD application is the QRate. So if the QRate is really high, then we can use the one-time pad to encode all the information, and all the information will be secure. But it's not the truth. So the QRate R is in the real life is limited by a lot of factors. So among them, one of the most important factors is the channel loss. So the channel loss is characterized by the transmittance eta, which is defined as the successful transmission probability from Alice to Bob. So what we are interested about is what's the relationship between R and eta. Like in the early days of QKD protocols, Alice and Bob encode the information into the coherent state, and like in the protocol proposed by Hana, Imoto, et al., they use the four coherent states, 0 pi, like 0 plus minus alpha, and plus minus I alpha to encode the four BB84 state. And Alice sends the state to Bob. For this kind of protocols, because there's a large basis floor, and we can, because there's a large basis floor, so the QRate of this, so Alice cannot send out the coherent state with a large intensity. The intensity should be scaled as the eta. So finally, the QRate of this kind of protocols will be O eta squared. But to deal with these issues, the decoy state method has to be introduced. So if we introduce the decoy state method, we randomize the phase of alpha, and we adjust the intensity of it. So with this kind of changing, we can use this method to estimate what's the Eve's behavior in the channel. So basically, it's a kind of partial tomography of the channel, and we can use this decoy state method. We can tightly bound the information leakage to Eve. And with this kind of method, the coherent state BB84 protocol QRate is going from O eta squared to O eta. And our problem is that it's O eta, the final QRate. Okay, there is some theoretical work which discusses about the upper bound of the point-to-point QKD protocols. So, just for this kind of protocols, Alice send out the signals and Bob to the measurement. And there are some works. The first work is done by TGW, and which is further improved by PLOB. And we know that for this kind of point-to-point QKD models, the QRates should be bounded by a linear function of eta. So it's a bad news. Like if all the QRate is bounded by a linear function of eta, and without any quantum repeaters, just as Marco mentioned, we know that the transmittance decays exponentially with the channel. It means that the QRate is at best decays exponentially with the channel. It's not a good news. So before we get to the pessimistic conclusions that all the QKD protocols hold this kind of linear bounds, we should consider the protocols that beyond the SKC model. So the protocols beyond the SKC models is protocols that both Alice and Bob both are sources and detectors. So now we want to discuss some examples of these protocols. So the first one is a BBM92 protocol. In this protocol, both Alice and Bob to perform measurement. And if we define the transmittance between Alice and Bob as eta, then the transmittance between Alice and Eve is square root of eta. At the first glimpse, we would guess that maybe the detected signals would scale with the square root of eta, but it's not the case. So if we carefully do research on this protocol, we can see that we need a coincident detection between Alice and Bob. So only if Alice and Bob have the detections simultaneously can they generate keys from the signals. So basically, we first do a square root on the eta, and we square it again. So it goes back to the O eta. So as a time reverse version of the BB92 protocol, we can consider MDI QKD protocol. In this kind of protocol, Alice and Bob send some qubit to Eve, and Eve performs an Bell-Sleigh measurement. With this kind of measurement, it still requires a coincident detection. It means that this kind of protocol cannot go beyond the linear bound. So as we can see, the coincident detection is a bad thing. We don't want these things happen. If we can make it a coincident detection to a single detection, it seems that okay, we can improve our Q rate. So let's take another example, which is named as MDI B92 protocol, which is proposed in the PhD thesis of forensics from Professor Nuckenhaus's group. And in this protocol, Alice and Bob encode the signals into the phase, into phase 0 and pi of the pulse. So Alice sends out either alpha or minus alpha, and this sends a signal to Eve. And Eve is supposed to do a single detection measurement. And we think this kind of we can say that in this kind of protocols, like the channel transmission loss is square root of eta, and there's only single detections. It seems that this kind of protocols can go beyond the linear bound. But if we consider a attack scenario, like if Eve performs an USD attack, so if want to discriminate the phase whether Alice send out is alpha or minus alpha, and the successful probability of it should be as a linear function of intensity mu. So to keep the protocol secure, you have to promise that Alice, the coherent states Alice send out, the intensity should be smaller than square root of eta. So with this kind of source flaw, the Q rate still scales with linearly with eta. So we take some early examples of MDI QKD or the E91 type QKD protocols. But we can see that for these three protocols, we have all we can have is the negative news. There's no breakthrough. So here we comes to the twin field QKD protocol, which is proposed by Marcos, and they make an observation that if we introduce the decoy state method, just like the original BB84 does, if we introduce the decoy state method, that is to randomize the phase and modulate the intensity of it, maybe we have the potential to go through or go beyond the linear bound. And in this protocol, they use the BB84 type encoding. So they encode the information into the plus minus alpha and the plus minus I alpha, and they use two bases. And this is a hot topic at this moment in the MDI QKD field. But at that moment, the security proof of this type of protocol is still open. So what we have done is that we based on the original MDI B92 protocol, and we take the sort of decoy state method, and we generalize the picture, and we design a so-called phase matching MDI QKD protocol. And in this protocol, Alice and Bob encode the information, alpha and minus alpha. And after that, Alice and Bob generate a random phase on it. And they send it to Eve, and Eve do a single detections and announce the result. And Alice and Bob will do the post-selection. They choose the signals with phi equals to phi b. And the name of phase matching is a variant of phase encoding. So with the name phase matching, we want to catch, it's a more technical name. We want to catch two key points of this kind of protocols. So the phase matching means that like the phase reference of Alice and Bob should match in this type of protocols. If the phase of Alice and Bob does not match, and there's a phase drift, there will be a large phase error, a large bit error. And our protocol is a natural extension of the MDI B92 protocol, and in the physical implementation, it's similar to a one basis twin field QKD protocol. But later I will show that for these kind of protocols, you cannot consider the security from the view of the single photon source, and this is a key point of the name phase matching, because originally when you use the name phase encoding, basically you mean the relative phase encoding. You encoded the phase into the single photon component of the signals. But in this type of protocols, if you announce the phase, then there will be no single photon component, and we should take it as a variant and of the coherent state-based QKD protocols. And for this kind of protocols, I will briefly introduce the security of it. So to introduce the security of it, I will first introduce an entanglement-based view of this kind of protocols. So we consider the signals with the same random phase. So phi equals to phi b equals to phi. For these signals, it's equivalent to think that a virtual trusted party, Charlie, he will prepare a coherent state with random phase, and he send it to split it and send it to Alice and Bob. Alice and Bob will use the ancillary qubit to do the control phase modulation, and after that, Alice and Bob send out the two optical modes to Eve to do the detections, and Alice and Bob will measure the Z basis to generate keys, and they will estimate the ZZ error and XS error. So our security proof is based on a Schroeder scale entanglement distillation way, and the key rate is take the Schroeder scale formula, and as we can see, the error Z error can be directly estimated from the protocol. So basically, you can calculate the EZ directly from the original protocol. But and the key point of our protocol is to estimate the overall phase error, EX. So how to estimate this EX is our core issues. To do this, we first notice that the pulse Charlie sent out is a phase randomized coherent state, which is a kind of mixture of the photon state. So we first do research, like what if Charlie sent out as a photon state? In this case, we can find a strong correlation between the ZZ error and XS error. So if Charlie sent out is a old photon state, then the Z error should be equal to the X error. If the Charlie sent out is even photon state, then the error should be the opposite. I think it is kind of a quality of the MDI interferometer. Okay, and if we can use the decoy state to estimate the EZ error and the yield of the K-photon component, we can estimate the overall phase error rate by just calculating the expected value of different photon component. And we can get back to the QCrypt formula again. So the QCrypt formula is taking such kind of form. So the EZ and the Q mu, the gain and the Q bar can be estimated from the experiment and directly from the experiment. And the EX can be bound by some decoy state parameters. But wait, when we discuss this kind of estimation, there's a really critical point that the phase announcement is made. So in this protocol, as we can show in the beginning, so in this protocol, Alice and Bob will announce the phase finally. So we know that the phase announcement does not commute with the photon number measurement. So it means that in this protocol, actually, there is no photon number, the concept of photon number. So we cannot think about the single photons and two photons and this kind of concept. So actually, we can find some BS attack which can show that this kind of photon number channel is invalid. So in our security proof, the core observation is that we can find an accelerate protocol which has without the phase announcement, and we can compare these two protocols, and we can see the overall observables, like the gain, the Z error and the X error keeps the same for these two protocols. And this is a technical point. For more details, you can refer to the papers. And this is a sketch of the security proof. And I will address some practical issues in the TF type or like PMQAD. So there were some practical issues. The first one is that if you choose the shifting conditions as phi equals to phi b, the post-selection will be infinitesimal. And to solve this, we take the similar idea as shown in the twin field. We introduce the phase slices. And with a sacrifice of the intrinsic errors, we can make the shifting factors to a reasonable value. And the second thing is that we can replace the continuous phase randomization to a discrete phase randomization. And second thing is a key point in this protocol, like there's a phase locking requirement. So in our protocol, we introduced some method shown, which is developed in the CVQD protocols. Like Alice and Bob can use the classical light to calibrate the phase reference deviation of each run. And they do not need to do a feedback control to make the phase lock. Instead, they can vary the shifting conditions. Like originally the shifting condition is phi equals to phi b, but now we can change it to phi equals to phi b plus delta, where delta is the phase difference. So the only requirement is that the phase in the channel cannot fluctuate too quickly. And with this, considering the practical issues, we do the simulations and with the practical factors here. And as we can see here, this protocol can surpass the so-called plot bound, linear bound, when the transmission distance is longer than 250 kilometers. And it can finally get the distance of about 500 to 400 to 500 kilometers. And if we set up a cutoff line as a place of 10 to the minus 8 for the real-life consideration, you can see that this protocol can basically double the transmission distance of the original protocols. And we think this kind of implementation can be really helpful for the future QD protocol design. And summary and outlook. The summary is that we can find a protocol which has a QRate dependence on the transmittance of the square root, and we strictly prove the security. And the outlook is that is the square root of eta the ultimate QRate bound. Can we say that for all the QD protocols, the square root of eta is the ultimate bound? There's no such works, and of course there are some other future works can be done. Like in this work we didn't consider the finite size effect, and we will introduce it. We will do this finite size analysis later. And another thing is that we take the way of inherent distillation analysis. There are some other ways which can make the security analysis tighter, and we are working on this. And this is Xiongfeng's group, and this is Xiongfeng, and this is me, and this is Hongyi. And thank you a lot. And this is all my talk.
Thank you very much. Now the talk is open for discussion.
Yeah, thank you for this very nice presentation. It seems to me, but I would like to have your opinion, that this twin field protocol that you have analyzed here has similarities with a protocol for quantum repeater that was proposed by Professor Nicolas Sangoire, where, okay, in this repeater protocol, you had two memories at a distance that play the role of your sources, and indeed it is only a probability amplitude of a photon that goes to this central station. And for that reason, this quantum repeater protocol is more efficient than the normal twin photon protocols for repeaters. And do you agree that this one looks similar, or what are the similarities and differences?
Sorry, I'm not so familiar with the work you mentioned. As for my understanding, it's a work about quantum repeaters, is it?
Yeah, it's a quantum repeater protocol which looks very similar, but maybe I can show you later then.
Yeah, but in this protocol, the relay is untrusted, so it's controlled by the Eve. So maybe it's a difference between this protocol and the quantum repeater protocol, maybe.
I don't think so.
Oh, really?
But we should discuss that.
Okay.
Okay.
Discuss later.
Next, Norbert, please.
Yeah. Thank you very much for the nice presentation. At the end, you said something about that's not clear whether this order of square root eta is really an upper bound for all QKD protocols. But you have to be careful again. I mean, this is about QKD protocols with one intermediate station, right?
Right.
And if you go into one intermediate station, then you can again use the plop TGW bound arguments to argue that this is the upper bound. Isn't that correct?
Right. What we want to ask is just if there is no trusted relays and quantum repeaters, and can we do a better QRate performance? If
Yeah,
we have
but with
repeaters,
one
we can
station you cannot. We already know that. I would say with one station you cannot.
So there has been some works discussing about this kind of bounds.
Yeah, I think so.
Oh,
yeah.
really? Maybe I should learn it.
Let's talk more about it.
Okay.
Okay, now time is up. Let's speak again. Sorry.
Can I have one more question?
Very short, please.
Thanks, Pei. You mentioned that for your protocol, the fast drift shouldn't be too fast, right? Is there any typical value, like the threshold value for the fast drift?
So your question is there any protocols which can remove such requirement?
I mean, is there any typical value or the threshold value for your fast drift? Like under this, your protocol is okay, and up which is if the fast drift is larger than the threshold value, then your protocol is not work.
Actually, I do remember there were some parameters, but I didn't show it in the PPT. And I think maybe we can discuss it later with
Sure.
Marcos.
Thanks.
Yeah.
Okay, now let's speak again. And let's go to the next speaker.